Okay, so magnetic field pattern of a solenoid is really just coils added together, but of course usually a solenoid is made of one wire. There is just one wire that is coiled multiple times and then it comes out. So when current flows through, in this case it flows through this side and then it goes around and it comes back, and the effect is the same as having multiple flat coils stacked together. Okay, and of course you can see that the magnetic field, as I was saying, the field is really strong because all the fields are bunched up together inside and then outside, and you see that, hey, this looks really familiar, something you've seen before. It looks like the field pattern of a magnet, right? So the field pattern of a solenoid resembles that of a bar magnet. In fact, it's really similar. The north pole is here, the south pole is here. The only difference is that when we draw it, it kind of goes through and out. So you don't really have any of these like coming out of the middle kind of thing. But the idea is there, right? So the solenoid has two poles and can be used as an electromagnet. And of course, if you put a soft iron bar or soft iron core inside the coil, and it will be that much stronger because the coil itself will have all the domains aligned. When all the domains are aligned, it adds to the magnetic field, right? So anyway, as a shortcut, we can predict the direction of the magnetic field of solenoid using the right-hand grip rule, which is something that I've already taught you all in the previous section in magnetism, right? So the fingers will be the direction of current in the coil, and then the thumb will show you the magnetic field of the solenoid. Okay, so note that this is different from how we've been using it in this chapter. Okay, in this chapter, the thumb is always the direction of the current, right? And then the fingers are the magnetic field. In reality, you can do the same thing for this solenoid to find the direction of the magnetic field, just like what we did for the flat coil, right? So as it goes around, you keep pointing your thumb in the direction of the wire, you get your field out in the same direction. Honestly, to me, you should stick with that. But for this one, it's not confusing because no matter what right-hand grip rule, right, no matter what represents, you're still correct. So you can use this as well. So when you coil it, when your fingers coil in the direction of the current, so you can see here, if let's say the solenoid has is the wires coil this way, the current this way, your fingers point in the direction of the current. So you use your fingers first, point the direction of the current, then your thumb will point to the north side of the magnet. Okay, so the thumb will show you the magnetic field of the solenoid. Okay, so right hand grip rule works for this as well. Okay, in this when you flip, fingers represent current and thumb represents magnetic field. Okay, I hope that's not too confusing. Regardless, if you've mastered what I've said previously, you don't really need to know this, but it won't be wrong either. Okay, great. So let's jump to handout 2, question 3. Okay, so draw the magnetic field pattern surrounding the solenoids and determine the magnetic pole. Please go ahead and try this on your own. So first thing you want to do is identify the direction of the current. So for this one here, the current is going positive, negative, so you go conventional current. Conventional current means from positive to negative. Okay, so it flows out from positive. This one goes behind the bar and it goes in front of the bar here. It goes behind the bar and it goes in front of the bar here. So in front of the bar is down. Okay, I know you can't really see it. And then it comes out behind. Okay, so if you use your right hand grip rule here, your fingers curl around in a direction. So if this is the bar, my fingers curl around. So my thumb is pointing to the right. Okay, so this is my north, this will be my north, this will be my south. Okay, and then my field lines, my field pattern will look like this. So okay, it should be a bit more symmetrical. This way, just like a magnet. Okay, just like a bar magnet. Oops. And then here it's going into So you get something like this into oh man. Okay, you know they're not supposed to cross, okay, so it looks something like this. Okay, yeah, okay, so the next one here, this is the same thing. Can you imagine this is the same thing, except that so this is my coil. It's going in and out, in and out, in and out of the paper. This whole row is going into the paper because the X, this whole row is coming out of the paper. Okay, so if this whole row is going into the paper, that means that right hand grip rule, my magnetic field will be coiling clockwise around it. So it will look like coiling clockwise around it. So you get something like this, right? And then this whole row is going out of the paper. It's coiling anti-clockwise, like this. So anti-clockwise. This one is going clockwise. Okay. So if you look at that, then you see that the effect is everything inside is going to point to the left. So let me just draw the middle one first, and then I'll just draw the other coil, the other curved ones. Okay, honestly, you don't really need to squeeze so many in there. I think even one would have been fine. But I'm just gonna put it in there. Okay, and then the poles. This will be your north pole, this will be your south pole, because this is considered like a bar magnet. Okay, can you imagine this is a bar magnet? The field lines are coming out from the north side, going in from the south side. They're all pointing towards the north. Okay. So, okay. Back to the slides. How do you increase the strength of the magnetic field of a solenoid? Of course, the first thing again is you can increase the current flowing through the solenoid. You can increase the number of turns per unit length of the solenoid. Basically, for the same length, increase the number of turns. Or you can place a soft iron core within the solenoid. Okay, by placing a soft iron core within the solenoid, the soft iron core helps to concentrate the magnetic field lines within the iron core, making it a stronger field. You can also think about it as additional kind of fields going on, because the soft iron core becomes a magnet itself and adds to the field, right? So it concentrates the magnetic field lines and just amplifies it. Yeah. So what is the magnetic field pattern of magnetic fields due to current in a straight wire and solenoids? You know that already. In a straight wire, it curls around it, and then when you in solenoids, when you have a loop, it behaves a bit like an it becomes a bit like a magnet curling around the loop. You use your right hand grip to determine all of these directions. How can you increase or decrease the strength of the magnetic field? Okay, let's talk about increase. The first one you always go to is increase the current. Second one is increase the number of turns, specifically turns per unit length. And of course, you can use a soft iron core. Okay, so these are the things that we've covered in this lesson. Next lesson, we're going to move on to the next part.